Hello, everyone, and welcome to today's presentation. I'm excited to have you here as we explore the fascinating world of the system of particles and rotational motion. The title of our talk is System of Particles and Rotational Motion, and we'll also touch on related concepts that help us understand how objects spin and move in space. Over the next few minutes, we'll cover key principles, laws, and applications that make rotational dynamics so interesting and important. So let's get started. All right, let's take a closer look at this content slide. Here, we've got a list of sections numbered from 1 to 5, but interestingly, they're not in numerical order. For example, we see Section 4, then Section 2, then Section 5, followed by Section 3, and finally Section 1. This arrangement is intentional and highlights the importance of understanding how different sections connect within the overall structure. The key point here is to recognize that the sequence of these sections isn't linear or alphabetical. Instead, it reflects a specific flow or perhaps a hierarchy in our content. As we go through the presentation, keep in mind that the order of sections can be flexible and tailored to the message we want to emphasize. This slide sets the stage for understanding how each part, regardless of its position, contributes to the big picture. It's a reminder that sometimes the sequence is designed to challenge our expectations and encourage us to think critically about how information is organized. So, as we move forward, let's keep this in mind and see how these sections interrelate within the overall theme of our presentation. Now, let's take a closer look at Section 1. Here, I want to emphasize that our goal is to explain the key points thoroughly, but in a way that feels conversational and engaging. It's important to highlight the most critical concepts so that they stand out. As we go through this section, I'll connect these points back to the overall theme of our presentation, helping to reinforce how each piece fits into the bigger picture. Remember, the aim is to make these ideas clear and memorable, so I'll be focusing on clarity and relevance as we discuss each point. Let's start by talking about the reduced mass of a two-particle system. This concept helps simplify the analysis of two interacting particles by effectively reducing the problem to a single particle with a modified mass. It's a key idea when studying systems like binary stars or molecular interactions. Next, we move on to the motion of the center of mass. The center of mass essentially acts as a weighted average position of all particles involved, and its motion can often be treated as if all the mass were concentrated there. Understanding this helps us analyze the system's overall movement independently of internal forces. Now, regarding Newton's law for a system of particles, it extends the familiar principles of force and acceleration to multiple particles. Instead of looking at each particle separately, we use the center of mass and total external forces to describe the system's dynamics more efficiently. Finally, let's discuss the center of gravity and the center of mass. While they are often used interchangeably, the center of gravity considers the distribution of weight, especially in a gravitational field, whereas the center of mass is purely a geometrical and mass-based concept. Putting it all together, when we analyze a system of particles, understanding the center of mass helps us simplify complex interactions and better grasp the overall motion of the system. This perspective is fundamental as we delve deeper into the mechanics of multi-particle systems and their behaviors. Let's talk about a well-defined collection of particles. This means we're looking at a large number of particles that are grouped together in a specific way. These particles may or may not interact with each other, which is an important point. Sometimes, the particles influence each other, and sometimes they don't. Additionally, they could be connected to each other in some manner. This concept is fundamental because it helps us understand how systems of particles behave, whether in isolated groups or more complex arrangements. Recognizing these collections is essential for analyzing physical systems and their dynamics, especially as we explore different types of interactions and connections in the broader context of the presentation. The particle which interacts with each other applies force on each other. These forces of mutual interaction between the particles of the system are called the internal forces of the system. When we talk about these internal forces, we're referring to the forces that particles exert on one another within the system itself. These particles could be actual particles, like molecules, or they could be parts of rigid bodies, especially when these bodies are in translational motion. It's important to understand that these internal forces are what hold the system together or influence how it moves internally. So, when analyzing a system of particles, we need to pay close attention to these internal forces because they're crucial in understanding the overall behavior of the system. They differ from external forces, which come from outside the system, and together, these forces govern the dynamics we observe. In essence, internal forces are the mutual interactions that occur within the system, and recognizing them helps us better analyze and predict the motion and stability of the entire system. Now, let's continue with our discussion on the system of particles. On this slide, we're focusing on the term external force. So, what exactly does that mean? An external force is simply a force that acts on a particle, which is part of our system, but it comes from some other body outside of that system. In other words, it's not generated by the particles within the system itself, but rather by something external to it. This concept is crucial because when analyzing the behavior of a system, identifying external forces helps us understand how the system interacts with its surroundings. Recognizing these forces allows us to apply Newton's laws accurately and predict the system's motion or change. So, in summary, external forces are forces acting on particles from outside sources, and understanding them is key to analyzing the dynamics of any system of particles. The center of mass of a system of particles or a body is essentially the point inside or outside the body where we can imagine all the mass being concentrated. It's like a balance point, where the entire mass behaves as if it were concentrated at that single point. An important way to think about this is that at the center of mass, the algebraic sum of the moments of all the particles, meaning their masses times their distances from this point, adds up to 0. This concept is fundamental because it helps us simplify the analysis of how bodies move and respond to forces, especially when dealing with complex systems. Understanding the center of mass allows us to predict motion more accurately and connect the overall behavior of the body to this specific point, which acts as a sort of anchor for its motion. Let's talk about the center of mass for different shapes. The center of mass is a specific point where we can consider all the mass of a body to be concentrated. An interesting thing to note is that the center of mass doesn't always have to be inside the body itself. It can lie within the body, outside of it, or even on its surface, depending on the shape and mass distribution. This concept is really important because it helps us understand how objects behave when they move or balance. So, whether we're analyzing simple shapes or more complex bodies, knowing the position of the center of mass is key to predicting stability and motion. Let's continue exploring the center of mass and delve a bit deeper. When we talk about the center of mass, we're really referring to the point where the entire mass of an object can be considered to be concentrated. It's a crucial concept because it helps us analyze the motion of objects more simply. For example, when you're balancing a broomstick on your hand, you're actually balancing around its center of mass. Understanding how the center of mass behaves, especially when it shifts as the object moves or changes shape, is key in fields like engineering, physics, and even biomechanics. It's also important to realize that the center of mass isn't always located at the geometric center. It depends on how the mass is distributed within the object. By grasping these points, we can better predict how objects will respond under various forces, which ties back into the overall theme of understanding motion and stability in physical systems. Let's take a closer look at the center of mass. This concept is fundamental in understanding how objects behave when they move or are acted upon by forces. The center of mass is essentially the point where the entire mass of an object can be considered to be concentrated. Think of it as the balance point that determines how the object will balance or rotate. It's important because it helps us predict how objects will move in different situations, like in projectile motion or when analyzing stability. For example, a tennis ball and a bowling ball might seem very different, but their centers of mass help us understand how they will behave when thrown or rolled. In the bigger picture of this presentation, understanding the center of mass ties into how forces influence motion and stability. It's a key concept that bridges the principles of physics with real-world applications, from engineering to sports. So, grasping where the center of mass is located can give us a lot of insight into the mechanics of any object. Let's talk about the center of mass of a system of particles. An important point to remember is that the position of the center of mass doesn't depend on the choice of origin. This means no matter where you set your reference point, the center of mass remains the same. Now, if we consider two particles, the center of mass will always lie along the straight line connecting the two particles. It will be located somewhere between them, depending on their masses. In particular, when dealing with just two particles, you'll find that the center of mass tends to be closer to the heavier particle. This makes intuitive sense because the heavier mass pulls the center of mass toward itself. Understanding this concept is fundamental because it helps us analyze the motion of complex systems by simplifying them to their center of mass. This is a key idea that ties into the overall theme of understanding how systems behave dynamically. Now, let's consider what happens when we shift the origin to the center of mass, which we call point P. When we do this, an interesting thing occurs. The algebraic sum of the moments of all the masses in the system about this point becomes zero. Essentially, this means that the center of mass acts like a balancing point for the entire system. Furthermore, if the net external force acting on the system is zero, then the center of mass will stay in the same position. It won't move. This is a fundamental concept because it links the idea of forces and motion directly to the behavior of the center of mass. Throughout this presentation, we've been exploring how the center of mass helps us understand the overall motion of systems. Recognizing that shifting the origin to the center of mass simplifies our calculations and offers a clearer picture of the system's dynamics is really important. It highlights how the center of mass serves as a key reference point in mechanics. Let's take a closer look at the distinction between the center of mass and the center of gravity. Although these terms are often used interchangeably, they have subtle but important differences. The center of mass is the point where the entire mass of an object can be considered to be concentrated. It's a fixed point that depends solely on the distribution of mass within the object itself. On the other hand, the center of gravity is the point where the gravitational force can be considered to act. In many cases, especially near Earth's surface, the center of gravity coincides with the center of mass, but this isn't always true in environments with non-uniform gravitational fields, like in space or at high altitudes. Understanding this distinction is crucial because it affects how objects balance, move, and respond to forces. For example, when you're analyzing the stability of a structure or a moving body, knowing the position of the center of gravity helps predict how it will behave under different conditions. This concept ties into the overall theme of mechanics and stability, as it provides foundational insight into how objects respond to forces and how we can predict and control their motion. Recognizing the difference helps us design safer structures and improve our understanding of physical behaviors in various environments. Let's talk about the difference between the center of gravity and the center of mass. First, it's important to understand that the center of gravity of a rigid body can actually change depending on where you measure it from. In contrast, the center of mass remains constant regardless of where you are. This is because the center of mass depends solely on the distribution of mass within the body, not on external factors like gravity. Now, an interesting point is that the term center of gravity only makes sense when gravity is present. If there's no gravity, the concept loses its meaning since there's no down to define it. However, the center of mass is always a valid concept, no matter the presence or absence of gravity. Finally, when the gravitational field is uniform, meaning gravity is the same everywhere, the center of gravity and the center of mass actually coincide. This is a key idea because it simplifies many analyses in physics and engineering. Connecting all these points, understanding where these centers are and how they behave helps us analyze the stability, balance, and motion of bodies under different conditions. Newton's second law states that, when a force acts on a particle, this force is equal to mass times acceleration. Essentially, it tells us that the acceleration of an object depends directly on the force applied and inversely on its mass. Now, when we extend this idea to a system of particles, the law still holds, but we need to consider the forces acting on each individual particle and how they contribute to the overall motion. This means summing up all the forces and accelerations within the system to understand its behavior. It's a fundamental concept because it allows us to analyze complex systems by breaking them down into simpler parts, applying the same principles. Connecting this to our overall theme, Newton's second law gives us a powerful tool to predict and understand how objects move, whether we're dealing with a single particle or an entire system. Now, let's talk about the motion of the center of mass and how it is governed by Newton's law of motion. An important point to remember is that this law is only valid for a closed system, which means there is no change in the mass of the system during the motion. If mass is added or removed, then the law wouldn't directly apply in its simple form. Continuing from our previous discussion, when we consider a system of particles, Newton's law still holds, but we need to be a bit more careful in how we apply it. This is what we refer to as Newton's law for a system of particles, and it's a crucial extension because most real-world problems involve multiple particles interacting. Remember, the key idea here is that the motion of the system's center of mass can be analyzed independently of the internal forces acting between particles, provided the system is closed. This simplifies complex problems significantly and helps us understand the overall movement of the system in a more manageable way. So, connecting this back to our overall theme, understanding how the center of mass moves under Newton's law gives us powerful insights into the dynamics of complex systems, whether they're celestial bodies, vehicles, or even everyday objects. If a system experiences no external force, the center of mass will either stay at rest or keep moving at a constant velocity if it was already in motion. This means that, in the absence of external influences, the overall motion of the system's center of mass remains unchanged. The key point here is that the state of rest or uniform motion in a specific direction won't change unless an external unbalanced force acts upon it. This idea connects directly to the broader theme of conservation of momentum and Newton's laws, emphasizing how external forces are necessary to alter the motion of a system's center of mass. Let's take a closer look at the velocity, acceleration, and linear momentum of the center of mass. These concepts are fundamental because they help us understand how an entire system moves as a whole. First, velocity of the center of mass is essentially the average velocity of all parts of the system, weighted by their masses. It tells us the direction and speed at which the whole system is moving. Next, acceleration of the center of mass is the rate at which this velocity changes over time. Importantly, even if individual parts of the system move in complex ways, the center of mass can have a smooth, predictable acceleration. Finally, linear momentum of the center of mass relates to how much motion the system has overall. It's the product of the total mass and the velocity of the center of mass, giving us a clear picture of the system's motion energy. Connecting these points to the overall theme, understanding how the center of mass moves allows us to analyze complex systems more simply, focusing on their collective behavior rather than tracking every individual component. This makes it easier to predict motion and apply the principles of conservation in real-world scenarios. So, one important point to remember is that there is no external force acting in the horizontal direction. This means that the horizontal component of the center of mass's position will remain constant over time. Essentially, the center of mass won't shift side to side because nothing is pushing or pulling it horizontally. When we talk about a block sliding on a frictionless wedge, this concept becomes really useful because it simplifies our analysis. Since friction is absent, the only forces at play are gravity and the normal force from the wedge, which are perpendicular to each other. And because there are no horizontal external forces, the system's overall horizontal momentum is conserved. This ties into the broader theme of energy and momentum conservation in these systems, helping us understand how the block and wedge move together without external interference. Now, on this slide, we see that x1 represents the distance traveled by mass 1, which is moving to the right, while x2 is the distance traveled by mass 2, moving to the left. These distances are important because they tell us how far each mass moves from its starting point after the system is released. When we have these two masses connected to a spring, and we stretch the spring before releasing, both masses will start to move in opposite directions. This setup is a classic example of simple harmonic motion. The key point here is that the motion of these two masses is interconnected through the spring. As one moves to the right, the other moves to the left, and the distances they travel, x1 and x2, are linked through the spring's restoring force. This concept helps us understand energy transfer and how potential energy stored in the stretched spring converts into kinetic energy of the masses as they move. Connecting this to the overall theme, it highlights the fundamental principles of oscillations and energy conservation in mechanical systems. No external force in the x direction, so the x-coordinate of the center of mass of the Planckman system will not change. This means that if there are no forces pushing or pulling along the horizontal axis, the overall horizontal position of the combined system remains constant. In other words, the center of mass won't shift left or right. It's an important point because it highlights the principle of conservation of momentum in the absence of external forces. This idea connects to the overall theme of understanding how forces and motion interact, especially in systems like this where internal movements, like the man walking, don't affect the system's net horizontal position unless external forces come into play. So, even as the man walks along the plank, the system's center of mass maintains its position horizontally if no external force acts in that direction. Let's consider a mass, labeled m, that explodes into three smaller masses, which we'll call m1, m2, and m3. An important point here is that even after the explosion, the center of mass of the system remains at rest. This means that, despite the internal explosion and the masses flying apart, the overall center of mass doesn't move. It's a key concept because it illustrates the conservation of momentum in such an isolated system. So, no matter how the pieces fly off in different directions and speeds, the total momentum before and after the explosion stays the same, keeping the center of mass stationary. This example helps us understand how internal forces, like explosions, don't affect the system's overall motion, which ties into the broader theme of momentum conservation. Let's consider a simple two-particle system with masses m1 and m2 moving with velocities v1 and v2. Now, when we look at such a system, a very useful concept is the velocity of the center of mass. This is essentially the average velocity of the entire system, weighted by the masses. The key point here is that the velocity of the center of mass depends on both the masses and their velocities. It can be expressed mathematically as the sum of each mass times its velocity, divided by the total mass, m1 plus m2. This idea is fundamental because it allows us to analyze the motion of the system as a whole, rather than focusing on each particle separately. It's especially important when we talk about collisions or interactions, where understanding the motion of the center of mass simplifies the problem. Now, connecting this to the overall theme, recognizing the center of mass helps us understand how energy and momentum are conserved in the system. It provides a clearer picture of the dynamics involved, making it easier to predict the outcome of interactions between particles. So, in essence, the velocity of the center of mass is a crucial concept that ties together the masses, velocities, and the overall behavior of the two-particle system. Let's continue exploring the concept of the reduced mass in a two-particle system. As we discussed earlier, the reduced mass simplifies the complex two-body problem into an equivalent one-body problem, making calculations much more manageable. Now, on this slide, we're delving further into this idea, building on what we've already covered. Remember, the key point here is that by using the reduced mass, we can analyze the relative motion of the two particles without getting bogged down by their individual masses. This approach is especially useful in quantum mechanics and molecular physics, where interactions between particles are fundamental. So, as we go through this, keep in mind how the reduced mass connects to the broader theme of simplifying complex systems to better understand their behavior. It's a powerful tool that helps us bridge the gap between theory and real-world applications. Now, let's move on to Section 2. In this part, we'll focus on the key points that are essential for understanding the broader picture. As we go through this, I'll explain each concept thoroughly, but in a way that's easy to follow. The most important ideas here are the main themes that tie everything together and help us see how each piece fits into the overall story. Remember, the goal is to connect these details to the bigger picture we're building across this presentation. So stay engaged, and let's dive into these core concepts. Now, let's take a closer look at the parallel axes theorem. This theorem is really useful when we want to find the moment of inertia of a body about any axis, especially when it's parallel to an axis through its center of mass. It essentially helps us relate the moment of inertia about different axes. Moving on, we consider the rotation of a rigid body. Rotation involves the entire body turning about an axis, and understanding how this motion occurs is fundamental to analyzing many mechanical systems. Next, we see some examples of the moment of inertia for regular bodies. Knowing these values allows us to predict how these bodies will respond to forces and torques, which is crucial in engineering applications. Then, we come to the moment of inertia of a rigid body in general. This is a key concept because it quantifies how difficult it is to change the rotational motion of the body. The higher the moment of inertia, the more effort needed to accelerate or decelerate the rotation. Following that, we have the motion of a rigid body. This encompasses both translational and rotational movements and is essential to understanding the overall dynamics of rigid bodies. Next, the perpendicular axes theorem. This theorem states that the moment of inertia about an axis perpendicular to the plane of a lamina is the sum of the moments of inertia about two perpendicular axes lying in the plane and intersecting at a point. It's a handy tool when calculating moments of inertia for planar objects. Then, we look at the axis of rotation. Identifying the correct axis of rotation is key because the moment of inertia and the rotational dynamics depend heavily on this axis. Finally, we consider the center of mass of rigid bodies. The center of mass is the point where the body's mass can be considered concentrated for analysis purposes, especially when studying motion and stability. All these concepts tie together to give us a comprehensive understanding of rigid body dynamics, which is central to our overall exploration of rotational motion and mechanics. A solid body is essentially a material where the particles are arranged at definite positions. This means that the particles are fixed relative to each other, maintaining a consistent distance between them. Because of this, the size and shape of a rigid body do not change when external forces are applied. In other words, a rigid body does not undergo deformation. It remains unchanged under external influences. This concept is really important because it helps us understand how certain objects behave under various forces, especially in the context of structural integrity and stability. So, when we talk about rigid bodies, we're referring to those that maintain their shape and size no matter what external forces are acting on them. Let's dive into the concept of the center of mass of rigid bodies. The center of mass is a crucial point because it represents the average location of the mass distribution within a body. Essentially, it's the point where we can consider all the mass to be concentrated for analysis purposes. For rigid bodies, understanding the center of mass helps us predict how the object will move under various forces. When external forces act through the center of mass, the body tends to move without rotation. Conversely, forces applied away from this point can cause the body to spin or rotate. It's important to note that the position of the center of mass depends on the shape and mass distribution of the object. For simple shapes like uniform rods or spheres, calculating it is straightforward, but for complex bodies, we often use integration or summation techniques. Connecting this to the broader theme, knowing the center of mass allows us to analyze stability, balance, and motion more effectively. Whether we're studying vehicles, machinery, or even biological systems, this concept is fundamental in predicting and controlling movement. Let's continue our discussion on the center of mass of rigid bodies. In this slide, we'll delve deeper into some additional aspects that are essential for a thorough understanding. As we know, the center of mass is a crucial point that represents the average location of the mass distribution. Now, when dealing with complex bodies, especially those made up of multiple parts, it becomes important to understand how to determine the overall center of mass by considering each component. We'll explore how the position of the center of mass changes when the body moves or rotates, which is vital for analyzing dynamic systems. Remember, the key idea here is that the center of mass behaves similarly to a single particle with the total mass of the body, especially in translational motion. This simplifies many calculations in mechanics. Connecting this to our overall theme, understanding the center of mass allows us to predict how bodies will move under various forces, which is fundamental in designing stable structures and analyzing mechanical systems. So, keep these concepts in mind as we proceed, because they form the backbone of many advanced topics in rigid body dynamics. Let's continue our discussion on the center of mass of rigid bodies. In this slide, we'll delve deeper into some important concepts that build on what we've covered so far. As you recall, the center of mass is a crucial point because it simplifies the analysis of motion and force distribution. We'll start by revisiting the idea that the center of mass depends on the mass distribution within the body. This means that if you change the shape or the mass placement, the location of the center of mass shifts accordingly. It's essentially a weighted average of the positions of all the mass elements. Next, we'll look at how the center of mass moves. For a rigid body, its motion can be described as a combination of translation and rotation. The center of mass moves along a trajectory that depends on the external forces, following Newton's second law. Meanwhile, the body also rotates around its center of mass, which is an important aspect when analyzing complex motions. We'll also touch on the significance of choosing a reference point. The position of the center of mass relative to this point can be calculated using the coordinates of all the mass elements. This becomes particularly useful in practical applications, like designing mechanisms or analyzing stability. Finally, connecting this to the overall theme, understanding the center of mass helps us predict how bodies will behave under various forces, whether it's in mechanical systems, robotics, or structural engineering. It's a fundamental concept that underpins much of our analysis in dynamics. So, grasping these points will deepen your understanding of how rigid bodies behave in motion, and will enhance your ability to analyze and design mechanical systems effectively. Now, let's continue our discussion on the center of mass of rigid bodies. In this slide, we'll delve deeper into some important concepts that build on what we've already covered. First, remember that the center of mass is essentially the point where the mass of the body can be considered to be concentrated for analysis purposes. It's a crucial concept because it helps us simplify complex problems involving motion and stability. Next, we'll look at how to determine the center of mass for different types of bodies, especially those with irregular shapes. The key point here is that the position of the center of mass depends on the distribution of mass within the body, so understanding the body's geometry and mass distribution is essential. We'll also explore how the center of mass behaves when the body moves or rotates. For instance, in the absence of external forces, the center of mass follows a predictable path, which is the basis for many principles in mechanics. Finally, connecting this to the overall theme, grasping the concept of the center of mass not only helps us analyze motion, but also plays a vital role in stability and control of mechanical systems. So, as we move forward, keep in mind how these core ideas underpin many practical applications in engineering and physics. Let's continue our discussion on the center of mass of rigid bodies. In this slide, we'll delve into some additional aspects. First, remember that understanding the location of the center of mass is crucial for analyzing how objects move and balance. When we talk about rigid bodies, the center of mass can be found using various methods, depending on the shape and mass distribution. One key point to highlight is that for symmetric objects with uniform density, the center of mass often coincides with the geometric center. However, for irregular shapes or non-uniform densities, we need to apply the more general calculation methods. These methods involve summing up the moments of all the mass elements relative to a reference point. This concept connects directly to the overall theme of statics and dynamics, because knowing the center of mass helps us predict how an object will respond under various forces. Understanding the center of mass also plays a vital role in designing stable structures and in analyzing motion in real-world applications. So, grasping these principles not only enhances our theoretical knowledge, but also prepares us for practical problem-solving scenarios. Let's continue our discussion on the center of mass of rigid bodies. As we saw earlier, understanding the center of mass is crucial for analyzing how objects move and respond to forces. Now, in this slide, we're delving deeper into the concept. We'll explore how the center of mass can be determined for more complex bodies, especially when the mass distribution isn't uniform. It's important to remember that the position of the center of mass depends on the geometry and mass distribution of the object. We'll also look at how the center of mass behaves when the body is subjected to external forces, which is key for understanding stability and dynamics. By grasping these advanced ideas, we can better predict the motion of rigid bodies in real-world applications, tying everything back to the overall theme of mechanics and how we analyze and design moving systems. Now, let's continue exploring the center of mass of rigid bodies. On this slide, we're delving deeper into some of the key concepts that help us understand how the mass distribution affects the overall motion of rigid bodies. Remember, the center of mass is essentially the point where we can consider all the mass to be concentrated for analysis purposes. We've already discussed how to locate this point, but here, I want to emphasize that the position of the center of mass depends on how the mass is distributed throughout the body. So, if the mass shifts, the center of mass moves accordingly. This is particularly important when analyzing the stability and motion of objects, because the position of the center of mass influences how an object responds to forces and torques. For example, a lower center of mass generally means greater stability. Connecting this to our overall theme, understanding the center of mass is fundamental for predicting how rigid bodies behave under various conditions. Whether we're looking at simple objects or complex structures, pinpointing this point helps us simplify our analysis and improve our design or understanding of motion. Let's start by looking at the center of mass in the z direction. This is essentially the vertical component, which tells us how the mass is distributed along the height of the object. Moving on to the y direction, we're considering the lateral or side-to-side distribution of mass. And then, the x direction focuses on the front-to-back distribution. Now, when we talk about the position vector of the center of mass, we're referring to a vector that points from a chosen reference point, usually the origin, to the specific point where the mass can be considered to be concentrated. This vector is essential because it gives us a precise way to locate the center of mass in three-dimensional space. Finally, when dealing with a continuous mass distribution, things get a bit more complex. Instead of discrete particles, we have a continuous spread of mass, like a solid object. In this case, calculating the center of mass involves integrating over the entire volume, taking into account how the mass is distributed throughout the object. Understanding these concepts is fundamental because it helps us analyze and predict how objects behave under various forces, which is at the heart of mechanics and structural analysis. Let's start by looking at the three main types of motion we deal with in rigid bodies. First, we have pure rotational motion. This is when an object spins around a fixed axis without any translation. Think of a spinning wheel or a top. It's a very fundamental concept because it helps us understand how objects rotate. Next, we have the combination of translatory and rotational motion. This is common in real-world scenarios, where an object not only spins but also moves from one place to another. For example, consider a rolling ball. It both rotates and translates simultaneously. Finally, we have translatory motion, which is when an object moves from one position to another in a straight line, like a car driving down the road. All these types fit under the broader category of motion of a rigid body. Understanding these distinctions is crucial because it allows us to analyze and predict how different objects move in various situations. This foundational knowledge will help us tackle more complex dynamics problems later on. Today, let's discuss purely translational motion, which is a type of movement where the entire body moves without any rotation. In this case, every point on the rigid body shares the same velocity at any given moment. So, if you imagine pushing a box across the floor, all parts of that box slide together smoothly, without spinning or twisting. When analyzing such motion, we often simplify the entire body's mass and assume it's concentrated at a special point called the center of mass. This point effectively represents the body's overall motion. Additionally, the system of forces acting on the body can be thought of as a single force passing through this center of mass. This simplification makes analyzing the motion much more straightforward, because instead of dealing with multiple forces acting at different points, we consider just one force acting through the center of mass. This concept of translational motion is fundamental because it helps us understand how objects move in a straight line, and it forms the basis for more complex dynamics involving rotation and other types of movement. Now, let's explore how the system of forces acting on a body can be simplified. Essentially, any complex set of forces can be reduced to a single force. This single force might not pass through the center of mass, which is an important point to remember. Alternatively, these forces can be represented as two parallel forces that are not equal in magnitude. This simplification is very useful because it helps us analyze and understand the effects of the forces more easily. Moving further, we also see how translation and rotation come into play together. When analyzing a body's motion, it's often helpful to consider both these aspects simultaneously. Combining translation, which is the linear movement, with rotation, the spinning motion, gives us a complete picture of how the body behaves under various forces. This approach of combining forces and motions is fundamental in mechanics because it allows us to break down complex interactions into manageable, understandable components. It's a powerful way to connect the idea of forces with how bodies move and rotate in space. Let's take a closer look at this slide. Here, we see a fan rotating at a certain speed, with its center pivoted at a fixed point. What's important to note is that when analyzing the rotation of a rigid body like this fan, we can simplify the situation. Instead of considering all the complex forces acting on it, we reduce the entire body to just two equal but opposite forces that are not aligned, meaning they are parallel but unlike in nature. This simplification helps us understand the rotational behavior more clearly. The key concept here is that the rotation of a rigid body can be examined by focusing on these forces and their positions, especially their line of action and the resulting moment. When these forces are balanced in a particular way, they produce a turning effect around the pivot point. Connecting this to our overall theme, understanding how forces produce rotation is fundamental in analyzing the dynamics of rigid bodies. It helps us predict how objects like fans, turbines, or even machinery parts will behave under various force conditions. So, grasping this reduction to two equal but opposite forces gives us a powerful tool in our analysis toolkit. Now, let's explore the concept of a pivot. When a force is applied at the pivot point, the force exerted by the pivot is equal in magnitude but opposite in direction to the applied force. This balance is what allows the body to rotate smoothly around that point. As the body begins to rotate, the particles on it don't just move randomly, they move along a circular path. The center of this circle, which is crucial to understanding rotation, lies along what we call the axis of rotation. It's important to note that the body doesn't rotate in all directions at once. Instead, it moves within a specific plane that is perpendicular to this axis. We refer to this as the plane of rotation. Understanding this plane helps us analyze how rigid bodies rotate in real-world applications, whether it's machinery, vehicles, or even biological systems. This connection between the axis, the circular motion of particles, and the plane of rotation is central to grasping the dynamics of rotational motion. Let's take a closer look at some important points on translational and rotational motion. These concepts are fundamental because they help us understand how objects move in different ways. When we talk about translational motion, we're referring to movement where every point on an object moves the same distance in the same amount of time, like a car driving straight down the street. Rotational motion, on the other hand, involves objects spinning around an axis, like a spinning wheel or a merry-go-round. One key point to remember is that both types of motion involve different quantities and equations, but they are often interconnected. For example, the linear velocity of a point on a rotating object depends on its distance from the axis of rotation. This means points farther from the axis move faster in terms of linear speed, even though the entire object is rotating at the same angular velocity. Another important aspect is understanding how forces affect these motions. Forces can cause objects to translate or rotate, or sometimes both at the same time. That's why concepts like torque come into play when analyzing rotational motion. Connecting these points to the overall theme, mastering both translational and rotational motion allows us to analyze complex real-world systems more effectively, whether it's engineering a vehicle, understanding planetary motion, or designing machinery. Recognizing the similarities and differences between these types of motion helps us develop a more comprehensive understanding of dynamics as a whole. So let's talk about property that, by its very nature, opposes any change in its state of rest or uniform motion about an axis. This is a fundamental concept in rotational dynamics. You can think of it as similar to mass, but specifically for rotational motion. It's a scalar quantity, meaning it has magnitude but no direction, and its units are kilogram-meter squared, or kgm2. This property is known as the moment of inertia. And a quick formula to remember is I equals m times r squared, where m is the mass and r is the radius or distance from the axis of rotation. Now, when we discuss the moment of inertia about a rigid body, it helps us understand how that body resists changes in its rotational motion. It's a key concept because it influences how much torque is needed to produce a certain angular acceleration. Throughout this presentation, keep in mind that the moment of inertia is central to analyzing and designing systems involving rotation, whether it's machinery, vehicles, or any mechanical structure that spins or pivots. It's the rotational equivalent of mass in linear motion, providing insight into how objects behave under rotational forces. So, here we see that ρ represents the perpendicular distance from the axis to the ith particle, which has a mass m. Essentially, this distance is key because it helps us understand how each particle's position contributes to the system's rotational inertia. Now, when we talk about the moment of inertia for a system of particles, it's calculated by summing up the contributions from each individual particle. That's where the formula I equals the sum over all particles of m times ρ squared comes in. This sum essentially adds up all those tiny rotational contributions from each particle, giving us the overall moment of inertia. It's a really important concept because it allows us to analyze how a collection of particles, or a rigid body, resists rotational motion, which ties back to the overall theme of understanding rotational dynamics. Let's continue exploring the moment of inertia and its various aspects. In this slide, we delve deeper into the concept, highlighting how it is fundamental in understanding rotational dynamics. The moment of inertia, as you know, is essentially a measure of an object's resistance to changes in its rotation. It's like the rotational equivalent of mass in linear motion. When we talk about the moment of inertia, it's important to remember that it depends heavily on how the mass is distributed relative to the axis of rotation. This distribution impacts how much torque is needed to produce a given angular acceleration. In practical applications, calculating the moment of inertia involves summing or integrating the contributions from all mass elements, each weighted by the square of their distance from the axis. This is why geometry and mass distribution are crucial. By understanding these principles, we can better analyze and predict the behavior of rotating bodies, whether it's a simple wheel or complex machinery. This connection to the overall theme emphasizes how mastering these concepts enables us to design safer, more efficient systems that rely on rotational motion. Let's talk about the parallel axis theorem. Essentially, it tells us that the moment of inertia of a body about an axis parallel to one passing through its center of mass can be broken down into two parts. First, you have the moment of inertia about the axis through the center of mass itself. Then, you add the product of the body's mass times the square of the distance between these two axes. This is a powerful concept because it allows us to find the moment of inertia about any parallel axis, regardless of the body's size or shape. It's especially useful in real-world applications where the axis of rotation isn't necessarily passing through the center of mass. This theorem helps us relate different moments of inertia and understand how the body's distribution of mass influences its rotational behavior. Let's take a closer look at the perpendicular axes theorem. This theorem is a fundamental concept in moments of inertia, especially when dealing with objects that have perpendicular axes. Essentially, it states that the moment of inertia about an axis perpendicular to two other axes is equal to the sum of the moments of inertia about those two axes. Think of it this way. If you know the moments of inertia about the x-axis and y-axis, and these axes are perpendicular, then you can easily find the moment of inertia about the z-axis, which is perpendicular to both. This relationship simplifies calculations significantly, especially in complex geometries. This theorem is particularly useful because it allows us to break down a complicated problem into simpler parts. By understanding the moments of inertia along these perpendicular axes, we can more easily analyze how objects will respond to rotational forces in three-dimensional space. Connecting this back to our overall theme, the perpendicular axes theorem helps us build a more complete picture of an object's rotational behavior. It's a powerful tool that makes analyzing moments of inertia more manageable, especially when dealing with real-world applications where objects are rarely aligned with just one axis. Let's take a moment to talk about the radius of gyration. This is a really important concept because it helps us understand how mass, or a property like a molecule's structure, is distributed around a certain axis or point. Essentially, the radius of gyration gives us a measure of how far the mass is spread out from the center. Think of it as a way to quantify the size of an object in terms of its distribution. When the radius of gyration is small, it means the mass is tightly packed near the center. Conversely, a larger radius indicates the mass is more spread out. This concept is especially useful in fields like polymer science, structural engineering, and even in studying complex biological molecules. It ties directly back to the overall theme of analyzing how structures or systems behave based on their internal distribution. Understanding the radius of gyration helps us predict stability, flexibility, and other critical properties of the systems we study. So, it's a fundamental concept that underpins many of the advanced ideas we're exploring today. Let's take a closer look at the moment of inertia of some regular bodies. As we've seen, the moment of inertia depends heavily on how mass is distributed relative to the axis of rotation. Different shapes have different formulas because their mass distribution varies. For example, a solid sphere, a cylinder, or a rod each have their own unique moment of inertia formulas. Understanding these helps us analyze rotational dynamics more accurately. It also highlights how geometry influences rotational behavior, which is key to designing mechanical systems or understanding natural phenomena. So, recognizing these differences allows us to predict how various objects will respond when they rotate, tying back to the overall theme of rotational motion and inertia. Let's continue exploring the moment of inertia for some regular bodies. As we saw earlier, the moment of inertia depends heavily on how mass is distributed relative to the axis of rotation. Now, in this slide, we're extending that understanding to additional shapes and bodies. It's important to recognize that each shape has a specific formula, which comes from integrating the mass elements over the volume or area. For example, the moment of inertia of a solid sphere, a cylinder, or a rectangular plate varies depending on the axis about which we're rotating. These formulas are crucial because they help us predict how these objects will respond to rotational forces. Remember, the key takeaway is that the moment of inertia isn't just about mass, it's about how that mass is spread out. The further the mass is from the axis, the larger the moment of inertia, and the more torque you'll need for a given angular acceleration. Connecting this to our overall theme, understanding these moments of inertia allows us to analyze and design rotating systems more effectively, whether in machinery, structural components, or even in biological systems. So, keep these formulas in mind as tools to simplify complex rotational dynamics. Vamos continuar falando sobre o momento de inercia de alguns corpos regulares, e como essa propriedade varia dependendo de forma e de distribuição de massa. Como vimos antes, o momento de inercia é acute essential para entender como os objetos resistem as mudanças em seu movimento rotational. Aqui, vamos aprofundar pouco mais, especialmente para corpos que possuem formas geométricas regulares. Lembre-se que a forma e a distribuição de massa influenciam bastante no valor do momento de inercia. Por exemplo, cilindro, uma esfera ou uma placa possuem fórmulas específicas que levam em conta esses fatores. Esses exemplos são importantes porque mostram que podemos calcular facilmente o momento de inercia para diferentes corpos, desde que conhecemos sua geometria e massa. E isso é acute fundamental para analisar sistemas rotacionais na física e na engenharia. Então, ao entender esses casos, conseguimos aplicar esses conceitos em uma variedade de situações do mundo real. Now, let's move on to Section 3. Here, I want to highlight some key points that are crucial to understanding the bigger picture. As we go through this, remember that these concepts are interconnected and play a vital role in the overall theme of our presentation. I'll explain each point thoroughly, but in a conversational way, so it feels natural and engaging. The most important concepts here are the core ideas that drive our strategy forward, so I'll make sure to emphasize those. Connecting these points to the overall story will help us see how they fit into the bigger picture and why they matter. So, let's dive into this section and explore these ideas together. Let's take a closer look at the work-energy theorem. This is a fundamental concept that links the work done on an object to its change in energy. It's key to understanding how energy is transferred and transformed in mechanical systems. Starting with work, which is essentially the force applied over a distance, we see how it plays a role in various types of motion, including rolling motion. When an object rolls, work done by forces like friction or torque causes changes in its kinetic energy. Speaking of kinetic energy, we have the kinetic energy of rotation. This is the energy an object possesses because of its rotational motion, and it depends on its moment of inertia and angular velocity. Now, torque and angular acceleration are closely connected. Torque is what causes angular acceleration, similar to how force causes linear acceleration. When we have connected bodies, like gears or linked rotating parts, the torque applied to one affects the others, transferring energy throughout the system. Power is another crucial concept here. Power measures how quickly work is being done, so it's about the rate of energy transfer. High power means energy is being transferred rapidly, which is important in many engineering applications. We also consider the couple of forces, which is a pair of equal and opposite forces that produce rotation without translation. This is fundamental in analyzing rotational systems where forces create moments or torques causing objects to spin. Finally, this overview ties all these ideas together, emphasizing how work, energy, torque, power, and forces interact in rotational dynamics. Understanding these connections helps us analyze and design efficient mechanical systems, keeping the overall theme of energy transfer and efficiency at the forefront. A couple of forces is a very interesting concept in mechanics. It involves two forces that are equal in magnitude but act in opposite directions. Now, what's key here is that these forces are not just opposite, but they are also separated by some finite distance, meaning there's a specific perpendicular distance between them. This distance is crucial because it introduces a turning effect. Think of it like pushing on a door from opposite sides with equal strength. If you push at different points, the door will rotate. That rotation is caused by what we call a torque, and this entire setup is what we refer to as a couple of forces. This concept is fundamental because it helps us understand how objects can rotate without necessarily translating. It ties into the overall theme of understanding how forces produce different effects, either linear motion or rotational motion. So, a couple is essentially a pair of forces that, because of their finite separation, can cause rotation without changing the object's position. The perpendicular distance between the forces in a couple is known as the arm of the couple. This distance is crucial because it determines the magnitude of the turning effect produced by the couple. Now, it's interesting to note that the resultant force offered by a couple is actually zero. Even though there's no resultant force, the couple still creates a turning effect, which we call torque or the moment of force. Another key point is that the torque or moment of force generated by a couple about any point lying on the plane of the couple remains the same. This means that no matter where you choose to measure from within that plane, the turning effect stays constant. This concept ties into the overall theme of understanding how forces produce motion, especially rotational motion, and how couples are fundamental in creating pure moments without resulting in a net force. Today, we're going to talk about a fundamental concept in rotational dynamics, the ability of a force to produce rotation in a body about an axis. This idea is captured by what we call torque. Think of torque as the measure of how effectively a force can cause an object to spin or rotate around a specific point or axis. It's not just about how strong the force is, but also where and how that force is applied. The key points are that torque depends on two main factors: the magnitude of the force and the distance from the axis of rotation to the point where the force is applied. The greater the force, or the farther the point of application from the axis, the more torque you generate. This concept is essential because it helps us understand how different forces contribute to rotational motion, whether in machinery, sports, or even in our daily activities. So, as we move forward in this presentation, keep in mind that torque bridges the gap between force and rotational movement, giving us the tools to analyze and predict how objects will rotate under various forces. Let's continue exploring torque. As we discussed earlier, torque is essentially the rotational equivalent of force. Now, in this slide, we're delving deeper into some additional aspects that are crucial to understanding how torque works in real-world applications. First, the key idea is that torque depends not only on the amount of force applied, but also on the distance from the pivot point, which we call the lever arm. The longer the lever arm, the greater the torque for the same force. Next, it's important to recognize that the direction of the applied force matters a lot. Torque is maximized when the force is applied perpendicular to the lever arm. If you apply the force at an angle, only a component of that force contributes to the torque, which means the effective torque is reduced. Another point to keep in mind is the concept of equilibrium. When the sum of all torques acting on an object is zero, the object is in rotational equilibrium. This is a fundamental principle in mechanical systems and helps us analyze whether objects will start rotating or stay stable. Finally, understanding how torque interacts with other mechanical concepts ties back to our overall theme of mechanical advantage. By manipulating torque, through longer levers or applying force more efficiently, we can make tasks easier and design better machines. So, in essence, mastering these details about torque helps us optimize mechanical systems, making them more effective and efficient in various engineering applications. Let's now look at the calculation of torque. Torque is essentially a measure of how much a force can cause an object to rotate around an axis. When we talk about calculating torque, the key idea is to consider both the magnitude of the force and the distance from the pivot point where the force is applied. This distance is often called the lever arm. The basic formula for torque involves multiplying the force applied by the perpendicular distance from the pivot to the line of action of the force. It's important to remember that the direction of the force and the angle at which it's applied can influence the effective torque. Understanding how to calculate torque is fundamental because it helps us analyze how different forces influence rotational motion in mechanical systems. Whether we're working with engines, levers, or gear systems, knowing how to quantify torque allows us to predict and optimize performance. So, by mastering this calculation, we're connecting the core principles of force and motion to real-world applications, which is essential in engineering and physics. Let's start with the relationship between torque and angular acceleration. Torque is essentially the rotational equivalent of force, and it's calculated as the moment of inertia multiplied by the angular acceleration. Think of it as how much rotational push is needed to change an object's rotational speed. Now, a key point here is that a body will stay at rest or continue rotating uniformly unless an external unbalanced torque acts on it. This is similar to linear motion, where an object keeps moving unless something forces it to stop or change direction. Furthermore, the rate of change of angular momentum is directly proportional to the net torque applied. So, if you apply a torque, you're effectively changing the body's angular momentum. This idea ties into Newton's law of rotational motion, which states that the angular acceleration of a body is proportional to the net torque and inversely proportional to its moment of inertia. In essence, understanding these relationships helps us predict how objects will rotate when forces are applied, and this principle is fundamental across many engineering and physics applications. When we look at the concept of work, it's more than just a physical activity or a task to complete. It's a fundamental part of how we engage with our environment and achieve our goals. Work can be seen as a process of applying effort, whether mental or physical, to produce a desired outcome. It's also closely tied to motivation and productivity, which are essential for personal and organizational success. In the broader context of this presentation, understanding work helps us appreciate the importance of efficiency, innovation, and resilience. It's about how we approach challenges and turn ideas into reality. So, when we think about work, let's keep in mind its role as a driving force behind progress and a key element in achieving our overall objectives. Let's talk about power. Power is a fundamental concept that influences how decisions are made and how influence is exerted within any system. It's not just about authority or control, it's also about the ability to shape outcomes and motivate others. When we consider power, we should think about its various forms, such as formal authority, expertise, or even the ability to persuade. Understanding power helps us see why certain individuals or groups can sway others, and how it impacts organizational dynamics. Throughout this presentation, we'll explore how power operates, how it can be used ethically, and how recognizing different sources of power can enhance our leadership skills. Ultimately, grasping the essence of power is key to navigating complex environments and driving positive change. Let's take a closer look at the work-energy theorem. This fundamental principle tells us that the work done on an object is equal to the change in its kinetic energy. In other words, when you apply a force to move an object, the energy you put into it shows up as a change in how fast it's moving. This theorem helps us connect the concepts of work and energy in a very direct way, making it easier to analyze physical situations. It's particularly useful because it allows us to predict the motion of objects based on the work done on them, without needing to track all the forces involved at every instant. Overall, it's a key idea that ties together the ideas of energy transfer and motion, which are central themes in our exploration of physics. Let's take a closer look at the motion of connected bodies. When we have multiple bodies linked together, their movements become interconnected, meaning the motion of one influences the others. This is a fundamental concept in mechanics because it helps us understand how forces and constraints affect the system as a whole. For example, if you think about a simple lever or a robotic arm, the way each segment moves depends on how they are connected and the forces applied. The key point here is that the connections, be they joints, hinges, or other constraints, dictate the possible motions and how energy is transmitted through the system. Understanding the motion of connected bodies is crucial because it allows us to predict the behavior of complex mechanical systems, whether they're in machinery, biomechanics, or robotics. It ties directly into the overall theme of analyzing systems dynamics, helping us design more efficient and predictable mechanisms. So, in essence, studying these motions gives us the tools to analyze and control systems with multiple interacting parts, ensuring they perform as intended. Now, let's continue exploring the motion of connected bodies. As we saw earlier, when two or more bodies are linked together, their motion becomes interconnected, leading to interesting dynamics. The key point here is understanding how the movement of one part influences the rest of the system. For example, when a link moves, it affects the position and velocity of the connected parts, which is crucial in design and analysis. We also need to consider how forces and torques are transmitted through these connections, shaping the overall behavior. Connecting this to our broader theme, mastering the motion of connected bodies, helps us design more efficient machines and mechanisms that work smoothly and reliably. So, always keep in mind how interconnected parts influence each other's motion. It's fundamental to understanding complex systems. Let's continue exploring the motion of connected bodies. On this slide, we're delving into how these bodies move together, which is a fundamental aspect of understanding complex mechanical systems. When bodies are connected, their motions are interdependent, meaning the movement of one influences the others. This interconnectedness can be seen in various forms, like linkages, gears, or even biological joints. It's important to recognize how forces and moments are transmitted through these connections, affecting the overall motion. The key point here is that analyzing these systems requires us to consider both the individual components and their interactions. This interconnected motion is crucial in designing efficient machinery and understanding natural movements. As we tie this into the broader theme of the presentation, remember that mastering the motion of connected bodies helps us predict behavior, improve system design, and optimize performance across many fields. Let's continue exploring the motion of connected bodies. In this slide, we're delving deeper into how connected bodies behave when they move. As you can see, the focus is on understanding the key principles that govern their motion, especially when multiple bodies are linked together. One of the most important concepts here is the idea that the motion of one part directly influences the others, which makes analyzing these systems both challenging and fascinating. We need to consider factors like the forces at play, the constraints imposed by connections like joints or rods, and how these affect the overall movement. Connecting this to the broader theme of our presentation, understanding the motion of connected bodies is essential for designing efficient mechanical systems. Whether it's robotics, machinery, or structural engineering, mastering these principles helps us predict and control how complex systems behave in real-world applications. So, as we move forward, keep in mind that the dynamics of connected bodies are fundamental to advancing our engineering capabilities and creating more sophisticated, reliable systems. Let's continue with the motion of connected bodies. As we delve deeper, it's important to understand how different types of connections influence movement. When bodies are linked, their motion is interdependent, and the way they move together depends on the nature of those connections. For example, if they're connected by a rigid link, their relative motion is restricted, and they tend to move as a single unit. On the other hand, if the connection allows some flexibility, like a joint with some slack, the bodies can have more independent motion. This concept is crucial because it helps us analyze complex systems by breaking them down into simpler connected components. It ties directly to the overall theme of understanding how forces and constraints shape motion. Recognizing these connections allows us to predict behaviors more accurately and design more efficient mechanical systems. So, when examining connected bodies, always consider the type of connection and the resulting constraints. These are key to understanding the overall motion. Now, let's continue exploring the motion of connected bodies. As we delve deeper, it's important to understand how the motion in such systems is interconnected. When two or more bodies are linked, say, by a joint or a rod, the movement of one directly influences the others. This interconnected motion creates complex dynamic behaviors that we need to analyze carefully. For example, if one part moves, it can cause a chain reaction through the entire system, affecting velocities and accelerations throughout. Recognizing these relationships helps us predict how the system will respond under various forces. This concept ties back to our overall theme of understanding mechanical systems in motion. By mastering the motion of connected bodies, we gain insights into more complex mechanisms, which is essential for designing efficient, functional machines. So, always think about how each component's movement impacts the whole system as we proceed. Let's take a closer look at the translational component VCM, which is the velocity of the center of mass, and the tangential rotational component that contributes to the motion. At the point of contact, point P, the net velocity is actually zero, which is a key concept in rolling motion. This means that at the exact point where the object touches the surface, there is no slipping. It's momentarily at rest relative to the surface. Now, point O only has translational velocity, representing the overall movement of the object's center of mass. Then, we have point Q, which is essentially the combination of linear and angular velocities. It's the resultant velocity that takes into account both translation and rotation. Finally, point T is interesting because its velocity is the sum of the linear velocity and the tangential velocity due to rotation, and this total is equal to twice VCM, or 2 VCM. This highlights how, in rolling motion, the velocities at different points on the object vary, but the relationship between them helps us understand the overall movement pattern. Understanding these components and their interactions is crucial for grasping the mechanics behind rolling motion, which ties directly into the broader concepts of kinematics and dynamics we've been discussing. Let's talk about the kinetic energy of a body in rolling motion. Essentially, it's made up of two parts: the translational kinetic energy, which is the energy due to the body moving from one place to another, and the rotational kinetic energy, which is the energy due to the body spinning around its axis. When an object rolls, both of these energies are at play simultaneously. So the total kinetic energy in rolling motion is simply the sum of these two components. Recognizing this helps us understand how energy is distributed in rolling objects, and it's a key concept when analyzing systems involving rolling motion, such as wheels, gears, or ball bearings. This idea ties into the broader theme of energy conservation and dynamics in mechanical systems. Let's move on to Section 4. In this part, we'll focus on the core principles that underpin our approach. I'll walk you through the key points thoroughly but in a conversational way, so it feels natural and engaging. It's important to highlight the most critical concepts here because they serve as the foundation for everything we've discussed so far. As we go through these ideas, I'll make sure to connect them back to the overall theme of the presentation, emphasizing how each piece fits into the bigger picture. Remember, understanding these core principles is essential for applying the concepts effectively and driving success in your projects. So, let's dive into the details and explore what makes this section so vital. Let's take a closer look at the comparison between linear and rotational motions. While linear motion involves objects moving along a straight path, rotational motion deals with objects spinning around an axis. Both are fundamental in understanding how bodies move in different scenarios. Next, we consider the equilibrium of rigid bodies. When a rigid body is in equilibrium, the net force and net torque acting on it are zero, meaning it remains at rest or continues to move uniformly. This concept is crucial for analyzing stable structures and mechanical systems. Moving on, there's an important relationship between angular momentum, denoted as L, and angular velocity, often represented as omega. Essentially, angular momentum is the rotational equivalent of linear momentum, and it depends on both the distribution of mass and how fast the body is spinning. We also have the concept of angular impulse, which relates to how a force applied over a period of time can change the angular momentum of a body. It's similar to linear impulse, but in the rotational context, and it helps us understand how to control or alter rotational motion. Now, an interesting connection exists between angular momentum and the kinetic energy of a rotating body. While both are linked to the body's motion, kinetic energy depends on the square of angular velocity, illustrating how energy and momentum are related but not identical in rotational dynamics. Next, we consider Newton's law of rotational motion, which states that the net torque acting on a body equals the rate of change of its angular momentum. This principle is fundamental for analyzing how forces cause rotational acceleration. Let's also look at the angular momentum of a rigid body as a whole. It can be viewed as the sum of the angular momenta of all its particles, often simplified using the body's moment of inertia and its angular velocity. The conservation of angular momentum is a key principle. When no external torque acts on a system, its total angular momentum remains constant. This conservation explains many phenomena, from spinning figure skaters to planetary motion. Finally, the angular momentum of a point mass is the product of its position vector and its linear momentum. Understanding this helps us grasp how individual particles contribute to the overall angular momentum of a system. To wrap up, these concepts form the foundation for analyzing rotational dynamics, connecting the physical principles with real-world applications and the overall theme of motion analysis. Let's talk about the angular momentum of a rigid body about a specific axis. Essentially, this is the moment of linear momentum of the entire body, but taken about that same axis. In other words, if you imagine the body moving or rotating, the angular momentum gives us a measure of how much rotational motion it has relative to that axis. It's important to understand that this concept connects directly to the linear momentum, but instead of just looking at how the body moves linearly, we're now focusing on how it rotates. So, the angular momentum is like a rotational counterpart to linear momentum, and it helps us analyze and predict the rotational behavior of rigid bodies in various systems. This idea is fundamental when we're studying how objects spin, how torque affects their motion, and how to control or predict their behavior in mechanical systems. Let's take a closer look at the relation between angular momentum, denoted as L, and angular velocity, which we often write as omega. These two concepts are closely connected in rotational dynamics. Essentially, the angular momentum describes how much rotational motion an object has, while the angular velocity tells us how fast it's spinning. Now, the key point here is that angular momentum is proportional to angular velocity, but this relationship depends on the object's moment of inertia. The moment of inertia, as we've discussed earlier, measures how mass is distributed relative to the axis of rotation. So, when we increase the angular velocity, keeping the moment of inertia constant, the angular momentum increases proportionally. Conversely, if the distribution of mass changes, altering the moment of inertia, this will directly affect the angular momentum for a given angular velocity. Understanding this relationship is fundamental because it links the rotational motion to the physical properties of the object, tying into the broader theme of how mass distribution influences rotational behavior. Today, we're going to discuss the angular momentum of a rigid body that is experiencing both translational and rotational motion. Now, as you might recall, angular momentum is a measure of an object's rotational motion about a point. For a rigid body, this concept becomes a bit more complex because the body can both translate and rotate simultaneously. So, when analyzing such a system, we need to consider how the overall angular momentum is composed of contributions from both the translational movement of the body's center of mass and its internal rotational motion around that center. A key point here is that the total angular momentum depends on the choice of the reference point. If we select the center of mass as our reference point, the calculations simplify because the translational and rotational components can be separated more easily. This slide emphasizes that understanding the angular momentum in this combined motion is essential for analyzing the dynamics of rigid bodies in real-world applications, where movement isn't purely rotational or purely translational, but a mix of both. By grasping how these components interact, we can better predict how objects will behave under various forces and moments, which ties back to our overall theme of understanding rigid body dynamics comprehensively. Now, let's talk about what happens when the net external torque acting on a body or a system of particles is zero. In this case, the total angular momentum of the system remains constant over time. This is what we call the conservation of angular momentum. Essentially, if no external forces are twisting or rotating the system, its angular momentum doesn't change. This principle is fundamental because it helps us understand how objects move when no external influences are in play. It's very similar to the conservation of linear momentum, but here, we're focusing on rotational motion. So, whether you're analyzing a spinning figure skater or the orbit of planets, this concept tells us that without external torque, their angular momentum stays the same. This ties into the overall theme of energy and momentum conservation in physics, highlighting the elegance and consistency of natural laws. Now, in this slide, we're looking at a moment when the external torque is zero, which means that the angular momentum stays constant. This is a key point because it highlights the conservation of angular momentum. When there's no external torque acting on the system, the total angular momentum remains the same over time. You can see that the angular speed, which we denote as omega, can change depending on the moment of inertia. For example, when she brings her arms closer to her body, her moment of inertia decreases. Because angular momentum is conserved, her angular speed must then increase to compensate. Think of the ballet dancer stretching her arms out or pulling them in. It's a perfect illustration of this principle. When she pulls her arms in, her rotation speeds up, demonstrating how a decrease in the moment of inertia results in an increase in angular velocity. This example emphasizes the core idea that in the absence of external torques, the angular momentum of a system remains constant, but the angular velocity can change based on how the mass distribution, or moment of inertia, varies. It's a beautiful demonstration of conservation in action, connecting the physics principles to real-world scenarios. Now, let's consider the Earth revolving around the Sun. The key point here is that the only force acting on the Earth in this scenario is the gravitational pull of the Sun. This gravitational force is what keeps Earth in its orbit. Since this force acts along the line connecting Earth and the Sun, it is what we call a central force. Because it's a central force, the torque about the Sun is zero, which means there's no change in the Earth's angular momentum due to this force. This leads us to an important principle. The angular momentum of Earth remains constant as it orbits the Sun. This is a direct consequence of the conservation of angular momentum, which we've been discussing. So, even as Earth moves along its elliptical path, its angular momentum stays the same, highlighting the fundamental role of central forces in orbital mechanics and the broader theme of conservation laws in physics. Now, let's take a closer look at the concepts of time, T2, and angular velocity. These are crucial when we're analyzing the conservation of angular momentum in a system, especially as it evolves over time. As the system changes, such as during a spin or a rotational movement, both the angular velocity and the moment of inertia can vary. It's important to remember that, according to the conservation of angular momentum, any change in the system's angular velocity must be balanced by a corresponding change in the moment of inertia, or vice versa. This means that if the system's shape or mass distribution shifts, the angular velocity adjusts accordingly to keep the total angular momentum constant. This principle is fundamental across many physical phenomena, from figure skaters pulling in their arms to spin faster to planetary rotations. It highlights how interconnected these quantities are. By understanding how T2 and omega-2 relate during these changes, we deepen our grasp of rotational dynamics and the overall conservation principles that govern physical systems. This is key to connecting earlier concepts we've discussed about angular momentum and how it remains constant in isolated systems. Let's start by looking at the fundamental relationship. Torque equals the moment of inertia times the angular acceleration. This is similar to Newton's second law in linear motion, but applied to rotational motion. It tells us that the torque applied to a body causes a change in its angular velocity, depending on how resistant it is to change, its moment of inertia. Now, moving on to the behavior of a body in rotational motion. An object will stay at rest or keep spinning at a constant rate unless an external unbalanced torque acts on it. This means that if no net torque is present, the object won't change its state of motion. Furthermore, the rate at which the angular momentum changes is directly proportional to the net torque applied. In other words, the net torque is responsible for changing the body's angular momentum over time. This concept is the rotational equivalent of Newton's second law, and it forms the core of Newton's law of rotational motion. It helps us understand how external forces influence the rotational state of objects, which is crucial in analyzing anything from simple spinning wheels to complex machinery. Now, let's look at how the resultant torque acting on a body about a specific point relates to its rotational properties. Essentially, this torque is equal to the moment of inertia of the body about that point multiplied by the angular acceleration. In other words, the greater the moment of inertia, the more torque is needed to achieve a certain angular acceleration. This concept is a rotational analog to Newton's second law in linear motion, where force equals mass times acceleration. Here, the moment of inertia plays the role of mass, and angular acceleration is, of course, the rate of change of rotational velocity. Recognizing this relationship helps us understand how objects resist changes in their rotational motion, which is fundamental in designing mechanical systems and analyzing dynamic behavior. So, in summary, this equation links torque, inertia, and angular acceleration, forming a core principle of Newton's law of rotational motion. Let's take a closer look at this fundamental equation. Tau equals I times alpha. Here, tau represents the torque, which is essentially the rotational equivalent of force. The I stands for the moment of inertia, which tells us how much an object resists changes in its rotational motion. And alpha is the angular acceleration, indicating how quickly the object's rotational speed is changing. This relationship is crucial because it links the applied torque directly to the resulting angular acceleration, scaled by the object's moment of inertia. Understanding this helps us analyze and predict how objects will behave when subjected to different forces in rotational systems. In the context of our overall discussion, this equation forms the foundation for exploring how various factors, like mass distribution and applied forces, affect rotational motion. It's a key piece in understanding the dynamics of rotating bodies. Let's take a closer look at the relation between tau and L. As you can see, tau typically represents a characteristic time scale, while L stands for a characteristic length. Understanding how these two are related helps us grasp the dynamics of the system we're studying. Essentially, the relationship often depends on the physical context, such as wave propagation or diffusion processes. For example, in many cases, tau can be proportional to L divided by some characteristic velocity. Recognizing this connection allows us to predict how changes in size or length influence the time scales involved. This is particularly important because it helps us understand the behavior of larger versus smaller systems and how their responses might differ over time. Overall, this relationship ties into the broader theme of how physical dimensions and time scales interplay within our models. Let's now focus on the equilibrium of rigid bodies. This concept is fundamental in understanding how objects stay at rest or move uniformly. When we talk about equilibrium, we're essentially referring to a state where all the forces and moments acting on a body are balanced. This means there's no net force causing the object to accelerate and no net moment causing it to rotate. Key points to remember are that for a body to be in equilibrium, the sum of all forces must be zero, and the sum of all moments about any point must also be zero. This principle is crucial because it allows us to analyze complex structures and mechanisms by breaking them down into simpler equilibrium conditions. Throughout this presentation, we've been exploring how forces interact within rigid bodies, and understanding equilibrium helps us predict the behavior of these bodies under various loading conditions. It's the cornerstone of statics and essential for ensuring stability and safety in engineering design. We know that angular momentum and kinetic energy are fundamental concepts in rotational dynamics. Angular momentum, denoted as L, essentially measures the rotational equivalent of linear momentum, how much motion an object has around a point or axis. Kinetic energy, on the other hand, relates to the energy an object possesses due to its motion, but in the rotational context. Understanding these two together helps us see the bigger picture of how objects spin and move. For example, a spinning figure skater pulling in her arms increases her angular velocity, which affects her angular momentum. Meanwhile, her kinetic energy also changes during this process, illustrating the connection between these concepts. Throughout this presentation, we've seen how angular momentum remains conserved in isolated systems, which is crucial in many physical scenarios. Kinetic energy, however, can be transformed into other forms, like heat or sound, especially during non-conservative interactions. Connecting these ideas, grasping the relationship between angular momentum and kinetic energy, allows us to better analyze rotational motion and predict how objects will behave under various forces and constraints. It's a key part of understanding the broader principles that govern dynamics in the physical world. Let's talk about angular impulse. This concept is key when analyzing rotational motion. Think of angular impulse as the rotational equivalent of linear impulse. It essentially measures the effect of a torque applied over a specific period of time. When a torque acts on an object, it causes a change in the object's angular momentum. This change is what we call angular impulse. The most important thing to remember is that angular impulse is equal to the change in angular momentum. So, if you know the torque applied and the duration it acts, you can determine how much the angular momentum will change. This relationship helps us understand how forces influence rotational motion over time, which is crucial in designing and analyzing mechanical systems. Connecting this to our overall theme, understanding angular impulse allows us to predict how objects will respond to applied forces in real-world scenarios, from machinery to sports. It's a fundamental concept that ties together torque, time, and rotational motion, giving us a complete picture of how systems behave dynamically. Now, let's talk about angular impulse. It is defined as the product of the torque acting on a body and the duration for which that torque acts. Essentially, it tells us how much rotational effect a force has over a certain period. If the torque remains constant, calculating the angular impulse is straightforward. Just multiply the torque by the time interval. However, in real-world situations, torque often varies with time, which complicates things a bit. In such cases, we need to consider the integral of torque over the time period to find the angular impulse. This concept is crucial because it links the applied torque to the change in the body's angular momentum, helping us understand how rotational motion evolves under different force conditions. Remember, The fundamental idea here is that angular impulse quantifies the total rotational effect of a varying torque over a specific interval. Now, let's take a closer look at the comparison of linear and rotational motion. Both types of motion involve movement, but they differ significantly in how that movement is characterized. Linear motion is straightforward. Imagine a car driving straight down a road or a ball rolling in a straight line. The key point here is that all parts of the object move in the same direction and at the same speed along a straight path. Rotational motion, on the other hand, involves an object spinning around an axis. Think of a spinning wheel or a figure skater twirling. Parts of the object move in circular paths around a central point. One important distinction is how we describe these motions. Linear motion uses parameters like velocity and acceleration along a straight line, while rotational motion uses angular velocity and angular acceleration to describe how fast something spins and how that spin changes over time. Understanding this comparison helps us see how these motions are related, but also how they differ fundamentally, which is essential as we explore the broader concepts of dynamics in this presentation. Let's continue our comparison of linear and rotational motion. As we delve deeper, it's important to remember that while these two types of motion are distinct, they also share some fundamental principles. For example, both involve concepts like velocity and acceleration, but how these are defined and applied can differ quite a bit. In linear motion, we're dealing with movement along a straight path, where quantities like displacement and velocity are straightforward. However, in rotational motion, these same quantities are represented differently. Think about angular displacement and angular velocity, which describe how an object spins around an axis. Another key point to consider is the way forces work in each type of motion. In linear motion, forces cause objects to accelerate along a straight line, following Newton's second law. In rotational motion, forces produce torque, which causes angular acceleration. This torque depends on the force applied and the distance from the axis of rotation. Connecting this to our overall theme, understanding these differences helps us analyze complex systems more effectively, whether it's a car moving forward or a wheel spinning. Recognizing the similarities and distinctions allows us to apply the right principles in the right context. Welcome to Section 5. Here, we'll focus on the core ideas that tie together the concepts we've discussed so far. This part is crucial because it helps us understand how all the pieces fit within the bigger picture. I'll be explaining the key points thoroughly, but in a conversational way, so it feels natural and engaging. I'll also highlight the most important concepts, making sure you grasp their significance. Throughout this section, I'll connect these points back to the overall theme of our presentation, emphasizing how they contribute to our understanding and application. So, let's dive into these ideas and see how they build on what we've already covered. Let's explore the difference between block sliding on a smooth inclined plane and a body rolling over a rough inclined plane. When an object rolls, it involves more complex motion compared to just sliding. Rolling incorporates both translational and rotational motion, which brings us to the concept of kinetic energy in rolling. Unlike pure translation, where the entire body moves uniformly, rolling involves rotational energy as well. This leads us to the idea of pure rotation, where all parts of the body rotate about a fixed axis without any translational movement. Now, the effect of an external force on a body is crucial. External forces can influence whether a body rolls smoothly or slides, especially depending on the surface roughness. It's important to distinguish between pure and impure rolling. Pure rolling occurs when there's no slipping between the body and the surface, meaning the point of contact is momentarily at rest relative to the surface. Impure rolling involves slipping, which introduces additional energy considerations. On the other hand, pure translation refers to a body moving without any rotation, just sliding along the surface. Finally, all these concepts tie back to the fundamental idea of a rigid body in motion. Understanding how forces and surface conditions affect the motion helps us grasp the underlying physics of rolling and sliding, which is vital for many practical applications. All right, let's delve into this slide. First, it states that angular velocity and angular acceleration are the same. Now, this is a key point because, in pure rotation, these two quantities are directly related. They change together, and their magnitudes are connected through the rotation rate of the object. Next, we see that in pure rotation, the acceleration of all particles is also the same in both magnitude and direction. This means every point on the rigid body experiences the same acceleration, which makes sense because the entire body rotates as a single unit without any deformation. Then there's the contrasting case of pure translation, where all particles move in a straight line with the same velocity. Here, unlike rotation, points move uniformly in a straight path, maintaining their relative positions without any rotation happening. Finally, the slide mentions a rigid body in motion. When a rigid body moves, whether rotating or translating, these principles help us understand how different parts of the body behave, ensuring the structure's integrity during motion. Recognizing these distinctions is essential because they underpin how we analyze and predict the motion of objects in mechanics. Now, let's look at how the velocity of any point on a rotating body is determined. The key idea here is that the velocity of a point depends on two factors: the distance of that point from the axis of rotation and the angular velocity of the body. In simple terms, if you imagine a point farther from the axis, it will move faster than one closer in, assuming the same angular velocity. Mathematically, we express this as velocity equals the distance from the axis multiplied by the angular velocity. This relationship is fundamental because it connects linear motion, how fast a point moves in a straight line, to the rotational motion of the entire body. It's also important to note that the linear velocity and acceleration can vary from point to point on the body, depending on how far each point is from the axis. So, points farther out will generally have higher velocities and accelerations compared to those near the axis. This plays a crucial role in understanding pure rotation, especially when analyzing rigid bodies in motion. In pure rotation, all points on the body move in a coordinated way, but their velocities depend directly on their distances from the axis. So, to sum up, the velocity at any point is proportional to its distance from the axis, and this concept helps us analyze and predict the motion of rotating bodies more effectively. Now, let's look at the second component, the velocity due to the rotation of the body about its center of mass. Every point on the body will actually have two components of velocity. The first one is the translational velocity, which is the same as the velocity of the center of mass itself. Think of it as the overall movement of the entire body moving forward or backward. The second component comes from the rotation. This is what makes the points on the body move in a circular path around the center of mass. When you combine these two components, translation and rotation, you get the total velocity at any given point on the body. This combined motion is what we see in rolling objects, where the body isn't just sliding, but also rotating as it moves forward. So, understanding these two velocity components helps us better grasp how rigid bodies move in real-world scenarios, especially in the context of rolling and other complex motions. Now, let's continue exploring the concept of a rigid body in motion. As we saw earlier, understanding how rigid bodies behave when they move is fundamental in mechanics. On this slide, we're delving into the details of how these bodies move, especially when they are in a state of rolling. It's important to grasp that when a rigid body rolls without slipping, there's a specific relationship between its translational motion and its rotational motion. This means that the point of contact with the surface is momentarily at rest relative to that surface, which significantly influences how we analyze the motion. We'll focus on key concepts such as the velocity of various points on the body, the role of angular velocity, and how these components work together during rolling motion. Recognizing these interactions helps us predict and understand the overall movement more accurately. Remember, the overall theme here is about integrating different types of motion, translational and rotational, to get a complete picture of how rigid bodies move in real-world applications. This understanding is crucial for designing mechanisms, analyzing vehicle dynamics, and solving complex engineering problems. Now, let's talk about the concept of rolling, which is a key technique in our overall approach. When we say rolling, we're referring to the ability to smoothly transition or move forward without interruption. It's about maintaining momentum and ensuring that progress feels seamless. This idea is crucial because, whether we're managing projects or developing skills, keeping that steady, continuous flow helps us stay efficient and effective. By mastering this concept, we can better adapt to changes and keep our initiatives on track, aligning perfectly with our broader goal of sustainable growth and improvement. Now, let's talk about pure rolling. In this case, adequate friction is present between the rolling surface and the body. This friction is actually crucial because it allows the rolling motion to occur smoothly without slipping. When the friction is just right, it enables the object to roll without losing contact or slipping on the surface. This is what we call pure rolling, where the point of contact is momentarily at rest relative to the surface. So, ensuring sufficient friction is key to achieving this ideal rolling condition, which is fundamental in many practical applications like wheels, gears, and even biomechanics. Remember, the right amount of friction keeps things rolling efficiently without unnecessary slipping or energy loss. Today, I want to talk about the concept of inadequate friction, which occurs when the relative velocity of the contact point on the roller with the body is greater than zero. Essentially, this means that the roller isn't rolling perfectly without slipping. When this happens, we describe it as impure rolling or slipping. In pure rolling, the point of contact between the roller and the surface is momentarily at rest relative to the surface. But in impure rolling, that contact point is moving, which indicates that some sliding is happening. This sliding or slipping affects the efficiency of the motion and the forces involved. Understanding this distinction is important because it influences how we analyze the motion and the forces acting on rolling objects. When slipping occurs, the behavior deviates from ideal pure rolling, and we need to account for this in our calculations and designs. So, in summary, whenever there's some slipping at the contact point, we have impure rolling, and recognizing this helps us better predict and control real-world systems involving rollers and wheels. Let's talk about what happens when the friction isn't quite enough to keep the rolling pure. Specifically, when the relative velocity of the contact point between the roller and the body is less than zero. This situation indicates that the contact point is slipping rather than rolling smoothly. We call this impure rolling or slipping. Essentially, instead of rolling without slipping, the roller is skidding a bit, which affects the motion and energy transfer. Recognizing this condition is important because it changes how we analyze the system's behavior. It's a key concept that ties into our overall understanding of rolling dynamics, especially in real-world applications where ideal rolling doesn't always occur. Now, let's wrap up with the concept of kinetic energy in rolling motion. As we've discussed, the kinetic energy of a body in rolling motion is actually composed of two parts: the translational kinetic energy, which is due to the movement of the center of mass, and the rotational kinetic energy, which comes from the body's rotation around that center. Together, these two components give us a complete picture of the energy involved when an object is rolling. Understanding this combined energy is crucial because it helps us analyze and predict the motion of rolling objects more accurately. This ties back to the overall theme of energy conservation and dynamics we've explored throughout the presentation. So, next time you see a rolling ball or wheel, remember that its energy is a blend of both translation and rotation, each playing a vital role in its movement.